This is lesson 3.1, the determinant of a matrix. It's our first lesson, obviously, of chapter 3, and chapter 3 is entirely about this idea of a determinant. Back in chapter 2, we actually saw this idea. Chapter 2, obviously, we looked at basic arithmetic with matrices, and one of the things that we did towards the end of the unit was looked at how to find the inverse of a matrix, and one of the steps in that process was to take 1 divided by a number and then multiply by that matrix that we had switched around to get the inverse. When we took 1 divided by that number in the denominator was the determinant. That's what we're going to talk about this chapter. So we're going to get into a little bit more depth in this first lesson of how to find a determinant for any square matrix. And then as we progress through the lessons in this chapter, we'll look at other things that we can do with the determinant. Ultimately, what are some applications of a determinant? So we're going to start by looking at a 2x2 matrix and how we find the determinant of that. And you may actually remember this from chapter 2. But if I have a 2x2 matrix, we'll just call this A, B, C, and D. The determinant, which we just say det of A, determinant of A, or you might see it as, it looks kind of almost like the absolute value of A, but it's the determinant of matrix A. We find it by simply multiplying the diagonals and subtracting. So in this case, we're going to take A times D minus C times B, or B times C. Order obviously doesn't matter here. So that's all we have to do to find the determinant of a 2x2 matrix. So in our example, to find the matrix of that, or to find the determinant of that matrix, we are going to take 2 times 5 minus negative 3 times 4, or 10 plus 12 is 22. And that's the determinant for that 2x2 matrix. Pretty straightforward. But what happens if I want to do a larger matrix? What if I have a 3x3, a 4x4, a 5x5? How do I find that determinant? Because obviously you don't just have diagonals that you can multiply like we do in the 2x2. So to do this, we need to first talk about what are called minors and cofactors. And so it says if A is a square matrix, then the minor Mij of the entry Aij is the determinant of the matrix obtained by deleting the ith row and jth column of matrix A. The cofactor Cij of the entry Aij is Cij equals negative 1 to the power of I plus j times the minor, or Mij. Clear as mud. All right, not that difficult actually. Let's create a matrix here and actually talk about what this is all saying. So I'm going to use kind of the very traditional setup here of just using A's with their subscripts as their locations. And let's talk about what is a minor and what is a cofactor. All right, so if, for example, I wanted to find the minor of entry 1, 3. So I'm looking at this entry right here, and I want to find the minor for that entry. What it says is I delete the row and the column that entry is in. So I'm literally crossing this off. I'm crossing this off. And what's left is a smaller matrix that I'm going to use to find the determinant. So I'm really just finding the determinant of A21, A22, A31, and A32. That's the minor. That's all it is. You take the entry that you're interested in, you cross off the row and the column, you find the determinant of what is left. For the cofactor, we then take the value of that, we take negative 1 to the power of I plus j, and then times that minor that we just found, okay? So we find that determinant first, that's our minor, and then we multiply that by negative 1 to the power of the sum of the row and the column that the entry is in. In essence, what this is doing, this cofactor, is it's just taking the determinant and it's either going to keep the sign or make the sign opposite based on where that entry is in the matrix. So another way to think about this is if I plus j is obviously positive, then it's going to be a positive 1. It'll keep the sign that it had. If it's negative, if I plus j is negative, then you'll have a negative 1. You're going to switch the sign. So in the entry 1, 1, that upper left corner, 1 plus 1 is 2, which is positive. It's going to keep the same value. But if I go over or down 1, I've now made that sum negative. And if I go over or down 1 more, it's back to positive. So in other words, if you think about where the entry is in the matrix, it's just going to follow this pattern of plus or minus through the entire thing. So you can either do this, the negative 1 to the power of I plus j, or, especially in a smaller matrix, you could just kind of calculate whether it's plus or minus in the matrix. And then based on that, if it's positive, you're going to keep the sign. If it's negative, you'll switch the sign of that determinant. Okay, so that's a cofactor and minor. So let's go ahead then and just do this for an actual matrix, just to kind of make this a little more clear. So we've got our matrix, our 3x3 matrix, and we are going to find the minors and cofactors for A11, A22, and A32. So for 1, let's start with the minor. So again, all that's saying is right now I'm interested in this entry right here, negative 2. So to find the minor, I'm going to cross off the row and the column that it's in, and I'm finding the determinant of the remaining inner matrix, that 5, 2, negative 3, 3. So in this case, 15 minus a negative 6 is a positive 21. So the cofactor then is, again, just taking negative 1, in this case to the power of 1 plus 1, or again, because it's in the first that first upper entry, it's just going to be positive, times 21, which is 21. All right, for A22, so now I'm interested in that middle entry of 5, which means I'm going to cross off its column and row. And so to find the minor of 2, 2, I'm going to take the determinant, find the determinant of negative 2, 6, 4, 3. And in this case, negative 6 minus 24 is negative 30. And the cofactor then is negative 1 to the power of 2 plus 2. Or again, if you think about I'm just going to write this right over here. This is plus minus plus. So it's going to be a positive value, which means we're just going to keep it at negative 30. Which you can see mathematically, obviously negative 1 to an even power is going to be positive 1 times negative 30. We keep the negative 30. And then lastly, for 3, 2, we have 3, 2 is going to be the negative 3 down at the bottom. We're going to cross off its column and row. Whoops, that would not be its row. This would be its row. And we are going to find the determinant of negative 2, 6, negative 1, 2. So negative 4 plus 6 is a positive 2. And then the cofactor. And again, I'll write this out mathematically, but if you want to use that shortcut, by all means, feel free to do that. So in this case, we are actually going to switch the sign then to a negative 2. So that's how we find minors and cofactors. Now, what is the point? Like, why are we finding that? Well, that gets into finding determinants of larger matrices. Again, 2 by 2, very simple. Multiply the diagonals, subtract. That's your determinant. But if I have a 3 by 3 or a 4 by 4 or larger, it's a little bit more complex, a little more complicated than the 2 by 2. Now in your book, you've got 2 different theorems. You've got one called the determinant of a square matrix and another called expansion by cofactors. I'm kind of skipping over the determinant of a square matrix because I really want to just get to the expansion by cofactors because that really encompasses both theorems. And all this says is that if you have a matrix A, and obviously a square matrix, so if A is a square matrix of order n, in other words, an n by n matrix, then we can find its determinant in really kind of one of 2 different ways. The determinant of A is given by the sum from I equals 1 to n of aij times cij. In other words, we take the entry in the matrix and we multiply it by its corresponding cofactor. And we do that for every number in this case, or every entry in this case, that is in that column. So we're going to call this a column expansion. So you pick a column in the matrix, and for every entry in that column, you simply go through this process that we described of finding the cofactors for all the entries in that column. You multiply those cofactors by the corresponding entry, add them all together, and that's your determinant. Now we can also do this with rows. So we could also write this as the determinant of A equals the sum of j equals 1 to n of aij, cij. So obviously in this case, what we're really saying then is that I is fixed based on the row that you pick, and then j is 1, 2, 3, 4, and so on until you've done every entry in that row. So this was a row expansion. Okay. So that's how you find the determinant for anything larger than a 2 by 2. So let's go ahead and we're going to do two different examples here for this. So in our first one, we're going to do a 3 by 3, and then we'll do a 4 by 4. So in our 3 by 3, it does not matter which row or column you pick any one. Just by convention, a lot of times we pick the first row. It doesn't have to be. You may notice numbers that might seem easier to work with in a different row or column, and so you may choose that as well. But I'll just use the first row here, which means we need to find the cofactors then for each of those entries, and then multiply those cofactors by the value of the entry. Okay. So for A11, we're going to start by finding the minor and then use the minor to get the cofactor. Now we've actually already done that. We did that up here because this is actually the same matrix that we're using in this example. So we already have the minor and the cofactor of 21. So I'm going to skip that work. We're just going to say that the cofactor is 21. But let's go ahead now. And so for A21, excuse me, 1, 2, we're going to start by finding the minor. So again, to get the minor, we are taking the entries that are remaining after we cross off the row and column that 3 is in. So we're going to take the determinant of -1, 2, 4, 3, which is -3 minus 8, or -11. And then again, just like we did before, the cofactor, -1 to the power of 3 times -11 is, in this case, a positive 11. So now, A13, the minor, so crossing off the row and column that the 6 is in, we're going to find the determinant of -1, 5 for -3, which is 3 minus 20 is -17. And the cofactor, we've got an even exponent, so we're just going to keep it even at -17, or keep it the same as -17. Okay, so we have our 3 cofactors. So now, to find the actual determinant of A, we need to take each of those cofactors, multiply them by their corresponding entries, and then add those together. So we are going to take, for example, A11 was -2. We're going to multiply that by 21. And then we're going to take the 3 times 11, and then plus 6 times -17. And so simplifying this out, we get a -42 plus 48 is 6 minus 102. So 6 minus 102 is a -96. So that would be our determinant for that matrix. Okay. So Again, pick any row, any column, it doesn't matter, and you're going to go through that process. So it's a bit of work. And so you can imagine then, as we go to the next example, where we're going to do a 4x4, it's a lot more work. Okay, so if I look at a 4x4, basically what happens here is I'm going to pick a row or column. And if, for example, if I pick this, this first row again, like I did before, I have 4 entries here. But when I cross off a row and a column, so if I look at A11, if I look at that first entry, if I cross off the row and column, what's left is not a 2x2 now, it's obviously a 3x3. So to find the minor and cofactor, to find kind of the determinant, I have to now deal with a 3x3, and in essence go through the entire process that we just did in example 3, just to get the number corresponding to the -2. Then I go across to 1 and I do the same thing. I have a 3x3, so now I have to go through the entire process that we went through in example 3. So in essence, it's possible that you'd have to do the example 3 4 times just to get the determinant for a 4x4. So now imagine a 5x5, a 6x6, a 7x7. You know, the almost kind of exponential growth of that work that you have to do just to get the determinant for those larger matrices. Now, thankfully, at least for some matrices, there can be shortcuts. If you think about the fact that when we find the determinant, when we actually get to this last step in the process of finding the determinant, we are taking the entries and multiplying them by the coefficients. So if those entries are 0, they're going to be 0, and we don't have to worry about that. So when I look at this matrix, I notice, for example, that this column right here has a whole bunch of zeros. So if I use that column to find my determinant, when I find the minor and the cofactor and everything else, you know, go through that whole process, any term that is a 0 doesn't actually matter, because when I get to that final step of taking Aij times the cofactor, I'll just get 0. So in this case, the only thing I really have to look at is this entry right here, okay? Which means I'm really just going through the previous example once. And let's go ahead and do that, and just, you know, just again to get a little extra practice with this. So I am technically selecting this third column, but again, I'm going to ignore all but the one entry, because those zeros, we can just ignore that, okay? So what I end up with then is if I cross off its row and column, I'm going to jump really kind of right to this last step here. So if I think about that process, I'm going to take the entry of 2. I'm going to multiply it by -1 to the power of, in this case, 5, times the determinant of -2, 1, -4, 2, 4, -3, and 0, -1, 1. Okay. So again, now I have to find the determinant of that 3x3 matrix, which is now going through the process that we just went through above. In this case, I am going to use the last row, because again, with that 0 in there, I can skip a step in this. I don't have to do the first term. I can just find the values at -1 and 1. And so at -1, I'm going to have the entry of -1, and then times that -1 to the power of 5, again, because we're third row, second column. And then times the matrix, or determinant of the matrix, we're -2, -4, and 2, -3. And then plus, so this is really the determinant of A that we're finding here, plus, and now I'm going to look at the 1, so that's my entry, times -1 to the power of 6, row 3, column 3, times the determinant -2, 1, 2, 4. hopefully I'm not going too fast here or combining too many steps, but I do want you to see that you know, where we did, kind of every step individually up in this previous example, and you may need to do that for a time until you're comfortable with this process. Eventually you can kind of jump to this last step and just really kind of write it all in one fell swoop. So in this case then, I have -1 times, let's see, I've got -1 times -1 times the determinant, so 6 plus 8 is 14. And then plus 1 times 1. I'll just write those just so we don't lose track of that, that those numbers were there. Obviously, we don't need to write those ones. And then times the determinant of -8 minus 2 is -10. So that gives us then positive 14 minus 10 is is 4. But don't lose track, right? This whole thing, and I'm sorry, this is not the determinant of A, is it? This is actually just the determinant of that inner matrix that we found. So this 4 that we just found is going through this process with this matrix, but we have one thing back here. I'm going to change colors here for a minute. This piece right here, we kind of lost track of that, and not intentionally. I knew it was there. I should have maybe warned you before I kept going. So everything that we did here was just finding this, right? This is all finding the determinant of this 3x3 matrix. So 4 is the determinant of that 3x3 matrix. Now we need to take that 4 and we need to multiply it by the -2. So our actual determinant of A is a -8, okay? Like I said, hopefully I didn't lose you in that, but just to recap, just real quickly here. So we looked at our matrix. In this case, I picked that third column because it had all those zeros in it and said because of all those zeros, I only need to focus on that 2. So I crossed off the row, I crossed off the column, and basically in this step right here, I just set up everything that we need to do to find the determinant. I took the entry of 2, and then I multiplied it by the -1 to the 5th power, and then times the 3x3 matrix that was still remaining after I crossed off the row and column. Okay. Then I just found the determinant of that 3x3. So again, this whole row is really just finding that determinant, which brought me to that value of 4. But then I have to come back and multiply it by that -2 that was sitting in front of that determinant to get my final answer for the entire 4x4 matrix. So again, apologize if I skipped maybe some steps there or maybe didn't make everything clear, but that's how you find the determinant for a larger matrix, is look for those opportunities to make your steps a lot simpler. All right. Now, obviously, if you didn't have any zeros, well, then it's a lot more work, and unfortunately, you've got to go through the process 4 times. All right, let's kind of switch gears for a minute here, and we're still dealing with finding or determinants of matrices, but let's talk for a minute about triangular matrices. So before we actually get into how we find determinants here for these, let's just talk about what a triangular matrix is. A triangular matrix happens when you have a diagonal of numbers and all of the entries on one side of that diagonal are zeros. Now, other entries, including values in that diagonal, can be 0, but you very clearly have, over on this side, you've got all zeros. In this case, we call this a lower triangular matrix because the actual values that are non-zero are in the lower part of that matrix. So lower triangular matrix. Oops. Triangular matrix. In the same way, we could have a matrix where you have all of your zeros in the lower half, which then, of course, we'd call this an upper triangular matrix. Now, it's not critically important that you know those names. It's just so you're familiar with them and just have awareness of that. But basically then what happens is when you have a triangular matrix, doesn't matter if your zeros are on the upper half, bottom half, it doesn't matter. The determinant then of that matrix, so the determinant of a triangular matrix is the product of the entries in the main diagonal. So it does not matter that we have values sitting in the other half, the other triangle of that matrix. You are just simply going to focus on the diagonal, and all you are going to do is multiply those values together, and that will give you the determinant. I'm not going to get into the math of this, but if you think about the process, if you think about how we find the determinant of a matrix, and especially if you think about even what we did in example 4, where we had all these zeros that allowed us to skip a lot of steps and skip a lot of things, what ends up happening is you end up with a situation where you just end up with the diagonals being multiplied together. Okay? So very simply then, if I have a triangular matrix like this, because again, we've got the diagonal, this all of these zeros, I just focus on those on that main diagonal, and the determinant of A is -2 times -2 times 3 times 1, which is 12. Be really nice if all matrices were triangular matrices, wouldn't it? Make our jobs a whole lot easier finding those determinants. All right, well, we're going to end there. So again, this whole section really just focusing on how to find a determinant of a square matrix. So practice that, and I will see you in the next lesson.